Look at this telemetry dashboard. A 2025 production system handling 100,000 daily queries routed to a trillion parameter cloud model generates over $30,000 in monthly operating expenses. Every token incurs a premium API fee, while the system waits on network round trips for answers. In 2026, enterprise teams realized this cloud dependency was entirely optional. They replaced expensive API calls with small language models, localized architectures containing fewer than 10 billion parameters that resolve 80% of standard production workloads. This 95% cost reduction is the result of distinct, optimized compression architectures, rather than simply making a larger model smaller. The era of defaulting to trillion parameter API calls has ended. Precision capability matching has replaced brute force. Parameters are the learned numerical weights that dictate a neural network's predictive capabilities. Trillion parameter models use this massive capacity to act as generalists, maintaining knowledge on disparate, unpredictable topics. But for high-volume, repetitive, domain-specific tasks, carrying this broad, generalist capability simply becomes inefficient, heavy computational deadweight. This split screen shows why breadth is unnecessary for specialized pipelines. On the left is the chaotic web of a generalist model. On the right, the tight, reinforced pathway of an SLM. On targeted tasks, a specialized 3 billion parameter model matches the accuracy of a 1 trillion parameter generalist. This matching performance occurs while running entirely on hardware the enterprise already owns. When executing predictable production logic, excess parameters represent a form of technical debt. Deploying an SLM does not require an enterprise to train a neural network from scratch. Instead, these models are built through knowledge distillation. This is training a smaller model to replicate a massive model's logic. In this diagram, a teacher model passes a condensed, filtered stream of logic to a student like Phi3 Mini. The process moves away from noisy internet scrapes towards highly curated datasets. The ingestion of textbook-quality synthetic data optimizes the student model's learning efficiency. This process retains over 90% of the teacher's capability at merely 5% of the parameter size. Focusing on high-quality data curation drastically outscales sheer data volume when you are engineering these systems for specific targeted reasoning tasks. The primary hardware bottleneck for local deployment is video RAM capacity. Extreme quantization provides the physical compression mechanism required to bypass this limit. This matrix shows the mathematical shift from high-resolution 16-bit floating point numbers to highly compressed 4-bit integers. This reduction is significant. A 7 billion parameter model drops from a 14 gigabyte footprint down to just 3.5 gigabytes. Crossing this 3.5 gigabyte threshold lets the model run on standard developer laptops instead of server farms. Further optimization is achieved through sparse attention, such as sliding window or grouped query attention. This restricts the model from evaluating every single token against all others, which drastically reduces the overall computational overhead. Compressing the weights and optimizing the attention mechanism changes the physics of AI deployment economics. Real-world enterprises must process both highly predictable repetitions and unpredictable edge cases simultaneously. A router architecture handles this. Incoming queries hit a central node, splitting traffic into two paths. It sends 80% of predictable queries to a local SLM, while the remaining 20% of complex tickets are automatically routed to a heavy cloud LLM. This architecture provides a 90% reduction in total operating costs while maintaining high accuracy. For code assistance and internal developer tools, the primary advantage is latency. Eliminating the network round trip drops response times to a locked 50 to 200 milliseconds. The router architecture optimizes an AI pipeline for the exact intersection of cost, speed, and reliability. Regulated industries face a final, non-negotiable barrier for AI deployment: data sovereignty. Legal, financial, and healthcare sectors cannot transmit sensitive operational data to external APIs. Healthcare providers utilize on-premise SLMs for HIPAA-compliant medical record extraction, as visualized by this closed-loop schematic. Because the model runs locally, zero data leaves the enterprise infrastructure, resolving the privacy bottleneck. At the extreme edge, 1 billion parameter models now run natively inside mobile applications without internet connectivity. Success in 2026 depends on precise architectural capability matching. High-level machine reasoning has been permanently decoupled from the cloud data center. how will the global software ecosystem adapt when autonomous 1 billion parameter reasoning engines run silently in the background of every local device?